Welcome back, everybody, and welcome to this session on autoencoders and the principal component analysis. So the principal component analysis, as we discussed last time, is a way to reduce the dimensionality of the problem. And it's a widely popular method. It's an unsupervised method, and it's often used in order to reduce the dimensionality of the number of features which you have. So what we are going to do today is actually to look at this link between autoencoders and the principal component analysis. And one of the things which we can prove, and which you will see today through the derivations, is that if we have a linear transformation between the input data and the output data of the autoencoder, then we can actually show that mathematically this is equivalent to a linear principal component analysis. There's also something which is called a kernel principal component analysis, and some of you may have heard of that. And I'm going to explain briefly what that means, because this is a technique which we will encounter in many, many types of applications. So the topic this week is thus a continued discussion of autoencoders. And an autoencoder network is a network that compresses typically high-dimensional data, input data, such as an image, into lower dimensional data. And there is some kind of embedding vector, and then there's a decoder network, which then decompresses a given embedding, and so this embedding vector, and then it brings it back to the original domain. So for those of you who are familiar with the singular value decomposition, we know that we can reduce the dimensionality of an object, like an image, by performing a singular value decomposition and just keeping some of the components. But then, since we have the matrices which perform the transformation, we can always reconstruct the full image or the full object, since we have all the vectors involved in the transformations. So a singular value decomposition can also be perceived and has been used widely as a way to compress images or other objects, so that you can have a blurred image, but then if you want the full image, you know exactly what kind of operations you need to do. The autoencoder is in a way a similar method. It belongs also to the class of unsupervised methods, because you can use this embedding to actually generate new images. So even though it can be used both as supervised, it's often used as an unsupervised method. And you can think of the decoder path as a way to also generate new images. Now, the method is extremely popular. So for those of you who are dealing with, let's say, CNNs and image recognition, autoencoders have been widely used. Now, pretty soon now, we are moving into generative methods. That means basically next week. And we are going to look at energy-based models, typically Boltzmann machines and similar generative methods. And then we are going to move over to variational autoencoders, which have some of the philosophy which we meet here. Except for variational autoencoders, we need to bring in more statistics, and we need to have some elements of Bayesian statistics as well. So generative methods are going to be the topic which we will deal with for the rest of the semester after next week. But today we will try to wrap up this discussions of autoencoders with programming examples, and then we will move over to generative methods, presumably next week. Now, I put in a lot of references here. You probably won't have time to read all of them, but there is a lot of activity on autoencoders, and it's a widely popular method in deep learning. And essentially what you will see is at the heart of all these methods. If you, for instance, go into any of these textbooks, like in Rashka's textbooks, or you look into Foster's textbook, which we discussed, you will find a feed-forward neural network at the heart, or a convolution neural network, or a recurrent neural network. So these basic deep learning methods, which we have been discussing till now, like an RNN, a CNN, and a feed-forward neural networks, they can be used as basic building stones. So that means that if you have written your own code and you want to reuse them, you can actually set up your own autoencoder. And it's actually not that difficult. And if you look at the PyTorch and TensorFlow examples, which I have, so I mainly put up TensorFlow and PyTorch examples in case you want to use them, you can actually replace the call to a neural network with your own neural network code and use the rest of the structure. So a typical autoencoder, as we said last time, there is a transformation of your input data. There is some matrix or some weight here, W. This can be linear, non-linear, complicated. That produces an intermediate part, which is normally called the code part, or just intermediate part. And then this intermediate part, together with its weights, which are trained by standard backpropagation. Then you have a decoder part, which maps via its own parameters, typically this weight matrix V, and its own biases. It then produces an output here. And the typical schematic setup of an autoencoder is you sending in some input. This could be number 4. And then you have an encoder part. There's some latent feature here where you actually try to reduce it down to the essential features. So this whole thinking of autoencoders in terms of dimensionality reduction is something which links extremely well with the principal component analysis, which is essentially a linear algebra-based method. So the basics of the method then is to have a part here, which is given like this. And at the end, we want to optimize some function which minimizes the difference between the input and the outputs. And a typical feed-forward or autoencoder contains a feed-forward architecture. And it has a given number of layers. And normally the first layer has the same number of neurons as you would typically have for the input observation. And then you keep reducing this one as you move forward to the middle of the network, which is often called also the bottleneck. So this feature generator where you do the dimensionality reduction has many, many different names. And then there is you would then typically reconstruct your data here. So this is the decoder part, and this is the encoder part, and this is normally called the feature generating layer. So with feature generating layer, you could now think of you having reduced the dimensionality of the problem. So this was roughly about the autoencoders. What I want to do now is actually go back to the principal component analysis and wrap up that discussion. So I'm going to repeat some of the things which we discussed last week. And then we are going to look at the 2 ways by which you would typically do it. One, which is known as the statistical path, and the other one, which is simply the singular value decomposition. And the singular value decomposition is often the one which is most used. So if you use scikit-learn or any of these libraries like TensorFlow or PyTorch, you will see that the principal component analysis uses the singular value decomposition. And when it performs a singular value decomposition, you keep only some of the properties. So let's take a look at that. And also, I have some program examples which hopefully can tell you or give you some intuition about what the principal component analysis is doing. So if you have, let's say, 100 features, maybe it's only the 10 first one or 10 features which are relevant. And this simplifies, obviously, your calculations if you want to train a feed-forward neural network. Instead of having 100 features, you can reduce it to 5, 10, and these are the most important ones, and they are used to fit a neural network. Okay, so let's bring back what we discussed last week. So I'm going to switch over to the whiteboard here. And then we're going a little bit back and forth between the whiteboard and the Jupyter Notebook. So what we did last week was actually to introduce the covariance matrix. So let's bring back some of these concepts. So we have the, if we now look at the link between principal component analysis, that one, so PCA and autoencoders. So one of the things which we did last week was to assume what we called a linear autoencoder. If we do that, we can show a direct link with the linear principal component analysis. Assume linear AE. So that means that when we optimize, so in an AE, an autoencoder, what you typically optimize is something like this. There's an argmin, and then you have some weight parameters, and I'm going to write this as a V tilde, simply because I'm going to use V for the singular value decomposition as well. So just to make a distinction. And the typical object which you then would optimize would be something like the mean squared error. And we have the input data. This is the data you want to reproduce. And then you have a model yi tilde squared. And then we made this assumption last time that this decoder, or this intermediate feature generating part, is given by a linear transformation of the input data, the data we want to reproduce. And then we had this function g, which now produces the y tilde. And now these are vectors or matrices. And this is given by this v tilde times h. And that means that our y tilde is something which we then can rewrite in terms of this affine transformation. We have two matrices which we multiply, and we multiply that with the input. So that means that the optimization problem which we end up with, argmin, we optimize with respect to these parameters, which are typically the weights and the biases of a neural network. And then we have the norm 2 squared, and we have y minus this v tilde times w and times y, and this is the norm 2 squared. So this is the quantity which we want to optimize. And if we do that, we can make a direct link with a linear PCA. And this is what I wanted to show you now. And we made this detour through the calculation and the setup of the covariance matrix and the correlation matrix, because that gives us the final recipe for linking the principal component analysis with this practical approach where we get rid of some specific features. Now, in this specific case here, which we have, let me also say something about the nonlinear properties. Linear, or what's often called a kernel PCA. So we are going to link with a linear PCA. That's what we are going to do. But we do also have kernel PCA. Now, a very simple way to understand that is, suppose you want to do a classification problem, and you have two classes. You have balls and stars, okay? Now, your data now looks like this. So you have the stars here, and this I'm going to put values here, 1, -1. So these are the stars, these are observations. And then I have a set of other observations. This is the other class, so this is a binary problem. And I would like to separate these two classes, okay? Now, you cannot draw a straight line here, right? Which separates the two classes. So you want to have a classification problem, crosses or balls, right? And if you look at this data here, that looks almost like an impossible quest if you now want to do a kind of linear approximation, because there's no kind of clear plane or line which separates the two classes. But you can transform this data easily, and that is called the kernel approach, which you will find in essentially all methods. If you go to linear regression, you will meet kernel linear regression, or just kernel regression. You will meet kernel lasso, kernel ridge. You will meet kernel support vector machines, kernel neural networks. There is a simple way by which you can transform this data and make it separable. Because now everything is just along this axis and they take the same value. But I could make a transformation of my data. do you see what kind of way I could transform this data? If you now look at the crosses, they are between -1 and 1. So we could give this a specific value. So this is the y-axis, and this is the x-axis. And these are values along the x-axis for these objects. Is there a simple way we could actually separate these two classes of objects? Easily, by a simple transformation. This is the basic philosophy of a kernel. If you think of a mathematical transformation here. So if you look at the values here for the crosses, they take values between -1 and 1. If I now perform a transformation where I multiply this with the value squared, if I do the value squared, then if you do that, so this is then the kernel. So these are actually the x values, and you will encounter kernels like this. So if I do that, I will transform my data set -1 to 1, and these crosses are going to lie, they will, I'm just going to write it schematically because the values themselves will actually lie along here, but the next ones, the circles, they will get bigger values. So they're not going to essentially lie around 0, but I would get circles which would then be something like this. And then I could actually just set up a straight line and separate the two faces. That is a very simple transformation, which is often used. Now, when you have multi-dimensional sets of data, then it's more difficult to see which transformation does the job. But this is an example of a kernel transformation where you simply multiply your data with some function. Now, what people end up doing, if you have a multi-dimensional object, is to multiply this with different types of kernels. You can have Gaussians, you can have exponentials, etc., etc. So we are not going to deal with the kernel part. We are going to look at the linear PCA and the linear autoencoder because they can mathematically be shown to be equivalent. But you see the kind of trick here. So if you meet this kind of wording like a kernel, whether this is a neural network or it's a support vector machine, a random forest or whatever, this is something which can make the classification problem much easier to train. Or just a simple transformation. Okay, so let's now go back to what we defined last time. So last time we defined the covariance of two vectors. So I'm going to use arrows to distinguish between vectors and matrices. In my lecture notes, you will see that these quantities are bold-faced. The vectors are lowercase letters, bold-faced, and the matrices are uppercase letters. But in my handwriting, it's difficult to see the distinction between lowercase and uppercase. So I'm going to put an arrow in order to indicate that this is a vector. So if we take two vectors, xi and xj, this was formally defined as 1 over n, a sum over k, and then we have the xki, so these are the elements of a specific vector, minus the mean value of that specific vector, multiplied with xkj minus xj. So let me just quickly remind you of these symbols. So we have this vector x of I, that is simply the quantity x0i, x1i, and this goes all the way down to xn minus 1 of I. This quantity, which we label as x of I, is just the mean value. And that has a sum over I. And then I have, j, from 0 up to n minus 1. And this is just the x of j of I. And then what we did was to define a new element, xki bar, or tilde, of xki minus the mean value but then we simply replace that one with xki here. So this is something which we called the centered element of that specific vector. And that simplifies the calculation of this covariance element. Now, keep in mind that this is, as you can see, as it's written here, this is nothing, this covariance, it's just a number. So it's not a matrix. So this is 1 over n, and then this is just x transposed times x of j vector. So keep in mind, this is just a vector, right? And times a vector, so it's an inner product. If I were to write it like xi times xj transpose, then this is a matrix. But just be careful with some of the notations here, okay? Because this is the outer product, if I write it like that. Is that okay? So I'm going to use, and I used that last week, this notation here to indicate a specific matrix element of the covariance matrix. So the case which we looked at last time, so let's quickly remind ourselves of it, was a matrix X. So this is hopefully a matrix. So you can, and this could contain the vector x0. I put an arrow on it, x1 arrow, like that. And the kind of notation which I used then was actually covariance of this matrix X. This is the same as this specific matrix, and we found then that this is given by 1 over n here. And let's just keep it, no, let's just keep it out. Just write it like that. This was the same as the variance, sigma 0. Along the diagonal, we have the variance. And then we have the covariance here between x0 and x1. And then this, the covariance is symmetric. So whether I write this one first with x1 or x0, it's exactly the same element. And you can see that if you go back to the definition here. So it doesn't matter whether you have xj or xi first. So this is a symmetric matrix. Now then you can build up a bigger matrix if you have more components. So in general, what we call the feature matrix or input matrix in general, this matrix X contains now many features. So every column here could be a set of features. So that could be, if you're looking at the cancer data, which we will remind you of a little bit later, there's a famous cancer data set, which is called the Wisconsin breast cancer data, which many of you have encountered. That has something like 30 features. So that means that there will be 30 columns containing then something up to 500 data about patients. And every column is then a feature of the tumor. So the matrix then is essentially going to be a matrix with the P columns. And these are what we normally call the features. And like that. And this is a matrix which has dimensionality n, which are the data entries, and p, the number of features. So this is a typical input data to our calculations. So that's the input matrix. And then we have the different vectors. And what we did then was actually to set up this covariance matrix. So now we have to be a little bit careful because here, this is a vector. But when you see the covariance matrix in general, so covariance matrix, so which we call this covar of X, this is now given by 1 over n, and now these are matrices. So this is X times X transpose times X. And that means that this object has a dimensionality of P times P. So these are the features of the problem. So if you're looking at the genomic classification of, let's say, the DNA, there could be millions of such features. And then the matrix becomes huge. So these are just some basic definitions. And then we also defined the covariance, the correlation matrix, and we defined also the variance. So remember now that these matrix elements, xki, which I also wrote originally like xki minus the mean value, and I've just translated. So every time you see one of these elements, this is a centered element where I subtracted the mean value. And for those of you who followed the course in previous course on machine learning, you will often have seen these as centering the data. And it's often a trick, it's a kind of scaling or centering, which is used to often reduce the dependence on outliers when you're training a specific model. So many algorithms do this by default. And this is something which many of you have already encountered. So we are going to use that because that also simplifies things. That means that the variance of a given vector, which I write like this, is actually given by 1 over n, and I'm summing over k, and I have these quantities xki squared. That's the variance. Now, the correlation matrix is often used because the variance itself can become a huge number. And we would like to scale it because then we can infer immediately from that number whether we have a huge degree of correlations or not. So the correlation matrix is often used, and this is something which many people actually plot or actually calculate in the beginning, just to get a feeling of which data are strongly correlated or not. As we mentioned last week, this housing data, we know that, intuitively, we know that the price of a house is strongly correlated with the size of the house, the number of rooms, number of bathrooms, etc. But it's probably less correlated with the color of the house. So the correlation matrix has matrix elements, xi, xj, which are defined as the covariance of xi of xj divided by the square root of the variance of xi and the variance of xj. So that means that on the diagonal, we will only have ones. So it can actually take values between 1 and -1, depending a little bit on the covariance element. But the variance is always a positive number. So the correlation matrix takes a very simple form with ones along the diagonal. It's a symmetric matrix. So if I write correlation of x, so this should be an uppercase letter, what I will get then are ones here along the diagonal, because then I divide by the variance. And then I would have the correlation matrix element of x0, x1. And this goes all the way up to correlation of x0, xp minus 1. And this should be like that. And this goes down here, and I have a correlation. This is just a single entry, so it's not a matrix element, it's actually just a number. So that's the correlation matrix. And this is something which many people actually use to get a feeling about the data. And if you have strong correlations, so if the events which you have, if we now assume that xi's and xj's are stochastic variables, and if all xi's are independent and identically distributed, which means we write it like IID, independent and identically distributed. So think of you having a stochastic event all the stochastic events which you have are generated by the same Gaussian distribution. Now, if that is the case, then the correlation matrix elements, or the covariance matrix elements, the non-diagonal ones, are exactly equal to 0. So that's a very important feature of stochastic data. So this is independent. This is identical, or identically, independent and identically distributed. So the D stands for distributed. If that is the case, then the covariance matrix elements, all the diagonal ones, and the correlation matrix elements are 0. So there is no correlation. So that means if that is the case, then the covariance of two vectors, xi, xj, and I is different from j, they are exactly equal to 0. So that means that the covariance matrix, so the covariance matrix then, will then just contain the variance, sigma 0, sigma 1, and down to sigma p minus 1 squared. And the rest of the elements are all 0. So then we have the variance, which simply measures the spread around the mean value of a given vector here. Okay? So these are just some concepts from statistics, which now turn useful when we are going to look at the principal component analysis. Because when we do the principal component analysis and we want to reduce the number of features, what we do then is that we look at the variance. Because if you now think of this as a diagonalization problem, if you look at this matrix, the covariance matrix, if I diagonalize it, that means that there is an orthogonal transformation, which makes my matrix diagonal. An orthogonal transformation preserves the eigenvalues, but it changes the eigenvectors. So think of the covariance as a matrix. So the covariance, the way we have defined it, is given by 1 over n of x transpose times x. So this is a matrix. And if we now want to find the eigenvalues, the typical strategy is to find eigenvalues. That means that what we would do then is to find a unitary or orthogonal transformation. So there is a matrix S, which times S transpose, or S transpose times S, which is now just the identity matrix. So in this specific case, this is a matrix which we have defined to have dimension P times P. So this should be an identity matrix of dimension P times P, okay? So if I then take and calculate the transform of this matrix, so this quantity which you see here, since we have this 1 over n, this is also a sample expectation value. So remember what we discussed last week, that the variance which we are getting here is actually the sample variance, because we have a sample of data. So we don't know the probability distribution, but we know the data which we have collected. That means that when we now are estimating things, so let me just set that up as a small intermezzo here, right? So keep in mind then, this is just a small aside before we move on. So if I calculate the true mean value, so which we often write like this, so we write it like an expectation value, and physicists love also this so-called Dirac notation for an expectation value. If we have a continuous distribution, we have an x, which is an element of a domain. There is a probability distribution for these x's. This is a lowercase x. And then we have the variable x of d of x. Alternatively, if we have a discrete probability, Then we would have a sum over all the x in a domain. We have this probability, so this is an x of I, and there is an x of I multiplied with an x of I. Now, in our case, we don't have the distribution. So normally, or we deal with a sample mean. Sample mean, which is given by a mu of x, which is 1 divided by n, and it has a sum over all the x of i's. And this does not need to be equal to the exact value. So suppose now that we know that this data follow a distribution, but we don't know the distribution. Then a little bit later, when we've done all this struggling, somebody tells us, hey, this is a Gaussian distribution, and you should get this x bar, but you are calculating a sample mean, and then we just invoke Bernoulli's law of large numbers. And hopefully then, when this little n goes to infinity, we are approaching the true mean value. But in general, our starting point is a lack of knowledge of the quantity which we have here, the probability distribution. So when you've taken a course in statistics, you have encountered the definition of a mean value or any moment. So you can actually have this to the power of n. And any of these moments can then be calculated, sometimes analytically, sometimes numerically. But when we run an experiment, we often don't have any idea what the probability looks like. And then we are just stuck with sample variables. That means that when you look at this one, it's pretty common to rewrite that. So the covariance of x, so this should be an uppercase letter, is now often rewritten as the expectation value of this quantity x transpose times x, which is the same as the sample covariance. It doesn't need to be the exact covariance because we have a limited set of data, okay? And you see that from the expression which we have for the covariance itself. If we go back a little bit and you look at the expression which we put up in the beginning, this one, in principle, there should have been the probability for xk of I and the probability for xk of j. But we don't know these probabilities in general. That's a pretty common setting when we have a data set. A common feature then is that you would collect the number of observations you make, suppose as a function of energy. If you're looking at an experiment at CERN, and there's somebody here in the audience who do experiments at CERN, and then you would simply have number of counts in a detector as a function of the energy. So what you would do then is to have energy on the x-axis and simply make a histogram where you have the number of counts. And then from that histogram, you could say, this looks like a Gaussian distribution. Let me fit it with a Gaussian. That's a typical approach which you would use when you have the experimental data at hand. Now, in our case, this is now given by this quantity. So and the x's are stochastic variables. They are by definition defined as that because we have an expectation value. And this expectation value, if the x's are not stochastic variables, then we normally call this an unbiased quantity because it's not biased by any probability. So when I now look at this matrix and I want to diagonalize it, what we could do now, and S is an orthogonal transformation. This is not a stochastic variable. So I would simply now calculate, if we now calculate this quantity here, times S. So I'm performing, you know that when you diagonalize, this is another aside. So if I have a matrix, let's call this a matrix A times a vector V, and this has some eigenvalue V. The standard procedure is actually to transform this matrix of S, and this matrix becomes a diagonal matrix, which then has all the eigenvalues, lambda 0 down to some lambda n minus 1. So there is some kind of magic transformation which does the job for us. So if we now look at this quantity here, what we are going to do now is to perform this transformation. So we transform our covariance into, so we are now performing this transformation, S transpose times X times X times S. And when I do that, I can actually rewrite this as S times the expectation value, because the transformation S is not a stochastic variable, so it does not enter an expectation value. And that means that if you now look at this quantity here, I can relabel that one, because this is now a diagonal matrix. And this would now be the covariance of Y. So where this Y is actually given by Y transpose times Y, which is the same as ST times X. So this is 1 over N, and this is now 1 over N here, X transpose times X times S. And this is the diagonal matrix. So what it has on the diagonals is actually the variance. I'm going to use the same symbol as I had before, because when I find the eigenvalues of a matrix, these eigenvalues are unchanged under an orthogonal transformation. What changes is the eigenvectors. So essentially, this is what we are doing with a matrix like this, okay? So what I do then, if I diagonalize my covariance matrix, I get the variance, and I get rid of all the non-diagonal elements. Now, the principal component analysis is us now looking at the total variance. So we sum up all the eigenvalues, which are the variances. And what we say then is that we keep only up to 95% of the total variance. So we keep the largest eigenvalues, the largest variances, those which give the largest spread. And we leave out the small eigenvalues. And you will see why by a simple example now. So let's look at that simple example before we take a small break, okay? So let's go back to the Jupyter notebook and see if we can build up some intuition about what we are doing here. So if we go to the Jupyter notebook, there is a simple example in the very beginning. And we are setting up, so here's a reminder of what we did last time and what we did now. But suppose this is the covariance matrix. I call this for sigma. So in this specific case, I'm having two vectors, x0 and x1. And each of these vectors has 10,000 points, okay? Then I calculate my covariance matrix with two vectors. So it's a multivariate normal distribution. And what I've done now is simply to fix the mean values of vector x0, if you follow that example on the whiteboard, which has mean -1, and the other one has mean 2. And these are just numbers which I put in, okay? I just made this up. And that means that I'm going to generate a multivariable Gaussian distribution, two variables, x0 and x1, where each one of them has 10,000 entries, okay? So you can see now that what I'm doing here is simply to define these matrices, and then I call a multivariate normal distribution. Instead of only one variable, I'm now having two variables or two vectors, okay? So I'm just running that one. Now, the first step is, as we discussed before, I'm going to subtract the mean value. And in this case, I just use pandas. So I take my matrix and subtract the mean values, which I have defined to be -1 and 2. So this is the next thing I do here. And then so this is the kind of scaling which we are doing. And now I print the covariance matrix. So pay attention now, because I put this value to 2. This value should also be 2. This should be 4, and this should be 2. But I'm only having 10,000 points. So when I call my random number generator, and I have only 10,000 points, I don't get exactly 4 and 2s. That's simply because I need more points. So I could now use 1 million points, then I would get values which would be closer to what I fixed. So I fix the values, but then my distribution doesn't give me exactly that because I have few points. Does that sound okay? Then what I'm doing is simply to do everything I did in the slides here. Now on the whiteboard, we just run and I plot. This is a distribution of 10,000 points for x0 and x1. These are the values of these vectors. And you see now this looks pretty, you cannot separate things properly, right? If you look at it. So you would say, I would need to keep the feature x0 and the feature x1. Suppose on the other hand that we go back a little bit. And you can actually also see this if you look at the eigenvectors. So let's just go down a little bit here. Why did this disappear? Okay, let's something which disappeared here. Okay, let's do that after the break here. Oops. Strange. Let's just restart it. So let's now do another case and we change that matrix, because then you will see intuitively the meaning of the principal component analysis. Let's just make the correlation matrix very small. So this is the covariance, which we put to 0.1. And then we assume that this quantity here on the diagonal is 0.2. So let's do that and see what we get then. So we now center it, setting up the same matrix as before. We calculate the covariance matrix, and you see now instead of 10, I have 10 point something. I don't get exactly 0.1, I don't get exactly 0.2, but this is the matrix I want to look at now. And now I plot these 10,000 points for the two vectors. Aha. What you see now is that most of the points lie in one direction. So the other vector, x1, is almost orthogonal to x0. So what I could say now is that, okay, let me skip that feature x1. And let me keep the one which has the largest eigenvalues. You also see that. So what you see now is that one of these vectors has a small spread. You see that? That has also to do with the fact that it has a small value. When I diagonalize, the variance is small. And you see that the spread is small. Whereas the other one, which has a big eigenvalue, has a big spread. So that means that there, I cannot simplify my features. I would actually have to take into account this big spread in the data. For the other axis, x1, as I called it, you see here that the spread is pretty small. So I could say now, let us forget it. And just use one feature, because most of the points lie now along the x-axis. And I just don't care about these small changes which I have around the x-axis for the other vector. Does that sound reasonable? This is the essence of the PCA and this dimensionality reductions. So you would keep some features which have a big spread, as you can see. So a big spread means also it has a big variance here. And you saw that if you look at the eigenvalues, it has a big eigenvalue. And you can read that off from the covariance matrix, where we put a variance to equal to 10. So we have a big spread. And then the other feature is something which I can neglect. So if you keep this message, then you see the basic philosophy of the PCA, or the principal component analysis. So the principal component analysis is simply you looking at the final eigenvalues and keeping the largest one, which represent the largest spread. Because if you have a large spread in your data, it's a set of data which you cannot ignore. You don't have a way to simplify it. If there is basically no spread, you could say, okay, I'm not caring so much about this dimension, which I'm leaving out, because there's not much spread here. Does that make sense? So play around a little bit with that, and you will see that if you have strong correlations in the data, as we started out with a covariance of 2 and 4 and 2 along the diagonal of them, then the eigenvectors are strongly mixed, because after the break, we are going to look at the eigenvectors of this matrix. And you will see that the eigenvector of one of these is strongly dominated by just one component. And that means that the other components is something which we can just leave out. So a PCA is essentially you diagonalizing the covariance matrix and keeping the largest eigenvalues, which are the same as the largest variance. This is a direct, implementation of it. You calculate the eigenvalues, but then historically, there is another approach, which is based on the reconstruction error, which we will also discuss after the break. So I went a little bit over time here, but I just wanted to show this example before we took a break. And then we just meet in 15 minutes, if that's okay. So what we did, well, in this specific case, was just to think of 2 vectors, each with 10,000 elements. And then we produced the covariance matrix, we just put in by hand here, that the covariance has fixed values. And I changed from 4 to 2, and I put these values to 10 and some small covariances, which means that there is not very much correlation between the 2 vectors x0 and x1. So one has a big, so the diagonal element is something which is proportional to the variance. And that diagonal element is large for one of these vectors, which means that we have a big spread in the data. And one of them has a mean value of -1. So the one with the variance element 10 has a small mean value here. So that means that when we then plot these different points, we end up with something like this. And then we see that there is not much spread along the y-axis, and we could think of getting rid of that degree of freedom. So if you then look at the eigenvalues, so if we collect all the steps, this is how you could make your own principal component analysis. But I wanted to show you how you can use scikit-learn to actually set in a condition on what kind of eigenvalues you want to keep. So in this specific case, what I'm doing now, I'm simply diagonalizing that covariance matrix, and I print the first eigenvector and the second eigenvector. But then I'm going to do a principal component analysis from scikit-learn. And here, I'm simply going to say that I want to keep the 2 components. And then I perform a PCA transformation, and you can see now that one eigenvalue, so this is the variance, is huge. The other one is very small. And you can see the mixing of the eigenvectors. So keep in mind now that if I do a dimensionality reduction, and if I leave out the second eigenvector, you see now that the first eigenvector has a very large component from the component x0, and it has a very small one from x1. So I could say that even if they're mixed, they have a small mixing, I just leave it out. Because think the probability of being in one of these now is given by this component squared. So if I square 0.99, I'm getting close to 0.99, whereas the other one, if I square that one, it's going to be 10 to the -4. So the probability of the second one is very, very small. So that means that I could now make an approximation where I simply say I just neglect this one and I just leave it out. So this is how you would actually use scikit-learn, and you specify how you want to do it. And if you now look at the way, we're going to come back to the classical PCA theorem. This is a case where I'm setting up a matrix which has 10 entries and 5 rows. You could think of that as the 5 features. And I just put up random numbers distributed according to the normal distribution. I subtract the mean value, as we did before. And then this is the centered result. And now I here actually perform a singular value decomposition, and I'm printing out the different components which you have. So the matrix is given by, so these are the components of the matrix. And that the PCA can assume that the data set is centered around the origin. And scikit-learn's PCA classes take care of centering the data for you, so if you do that. And however, if you implement PCA yourself, as in this example, if you use other libraries, don't forget to center the data first. So if you use scikit-learn, it actually does the centering by subtracting the mean for you. And once you have identified all the principal components, you can then reduce the dimensionality of the data set down to the D dimensions by projecting it into a hyperplane and defined by the first D principal components. And this is something which you could define here. You want to keep the first two ones, which are these two guys here. So of that matrix, which was a 10 by 5, that means that the covariance matrix becomes a 5 by 5 matrix. I keep only the two components which give the largest eigenvalues. And in that specific case, I now specify only two components, and you can see now that it keeps only the two first components. After fitting, you can then transform the data set so you can access the principal components using the component variables. And the way which you would typically do now, if you have, let's say, the cancer data, this is the famous cancer data, which many of you have met. So I'm training it with linear regression. I center the data. I can also now do a PCA. So keep in mind now that this data set has 30 features. And I keep only 2. And then I make a new fit with only 2 features, those which have the largest eigenvalues. And you see now this fit is actually not bad. It gives me a score of 96%, the accuracy. So if I take the full data, I get an accuracy of 99% on the training data. If I now just reduce this from 30 features down to 2 with PCA, I get 96%. So this is the accuracy where you just count the number of correctly classified events and divide by the total number of events. So this number should be 1 if you have a perfect fit. So when I do the training on the scale data with logistic regression, I get 99%, which is pretty good. It's very good. But you know that on the training data, I'm actually using all the data here now. On the training data, you can actually get a pretty perfect reproduction. But you see now that even with 2 features, I'm predicting what is a benign or not benign tumor with 96% accuracy. So if you can live with that accuracy, if you accept that, then this is a possible reduction of the dimensionality from 30 to 2. So you see the basic philosophy here? So the way you do this is actually that you keep those states which have the largest eigenvalues, which correspond to the largest variance, which is then the largest spread in data, where you have no possibility to make simplifications. So that's the overarching philosophy, right? That's why we use the covariance matrix, because that gives you a measure of the spread in the data. So if you have basically no spread, and the vector is orthogonal to the other ones, then you can often ignore a specific feature. And you can also, if you now look at other options, so this is with the library scikit-learn, you can then say that the cumulative sum of the variance should be 95%. So that means that you look at those features, you take the largest eigenvalues, and you sum till you have 95% of the total variance. And then you say that all the other ones, which have a very small variance, the small spread, as we saw in this, in the y direction up here, we say that we just neglect those degrees of freedom, and we focus on those which have a large spread in the data. And those are the features which we think will dominate the final fit of a specific model. And you saw that from the cancer data, we could get a decent acceptance ratio, although 96%, if you want to classify between a benign and a bad tumor, is perhaps not satisfactory. You would like to be 100% certain whether this is a good one or a bad case. So this depends from case to case, what you accept as a good fit. So what many people do is that they play around a little bit with the dimensionalities and try to find the optimal one, where you, at the end, strike the balance between what you accept or not. Because at the end, it's you who decides what is acceptable or not. Now, there's one thing I wanted to end this part with, and that's actually going back to the what we call the classical PCA theorem, and the link, and also link this with the singular value decomposition. So let's go back to the whiteboard. So I hope this simple example gives you a feeling of what the PCA is doing. And now what I wanted to is actually to give you this link with the singular value decomposition and also going back to autoencoders. So what we have done here is to find a matrix which diagonalizes the covariance matrix, and that gives us the variance here. And the standard PCA is that we can make a truncation now up to a specific total sum, which is below, let's say, 95% or 90%. And those features which they represent are the features which we would keep. But keep in mind that any eigenvector which you get, because the eigenvector is now a linear combination of all the features. So even if this eigenvalue is now isolated and you have zeros around, the eigenvector will contain some information from all the other features. But there will be a feature for that specific state, which is a dominant one. So there is often a coefficient in the eigenvector expansion because you're diagonalizing, so you have a linear expansion in terms of all the features which you have. Then you would typically look at those which give the largest components to that vector. And hopefully one feature stands out in this diagonalization process for each eigenvalue. If not, an eigenvalue may represent a linear combination of several features. So this is just an eigenvalue analysis problem. But let's now, before we go to the classical PCA, let's take a look at the link with singular value decomposition. So this is just a small intermezzo. Now, the thing which is neat with the singular value decomposition is that we can decompose any matrix. So the matrix X, which we had, our data, can then be written out in terms of an orthogonal matrix times a diagonal matrix, which I'm now going to call sigma, just to distinguish it from the diagonal one I had before. And this matrix, the total one, has dimensionality again, n times p. This matrix U is an orthogonal matrix, which means that it's given by the identity matrix, but it has dimension n times n. This matrix V is also an orthogonal matrix, and that has dimensionality P times P. And this matrix sigma contains the singular values. And these singular values are 0 for all values up to the rank, P minus 1, and then it has just zeros, as we discussed last time. So this matrix has a dimensionality of n times P. Now, if you do a singular value decomposition now of your covariance matrix, you can read off the eigenvalues immediately as the singular values. So this is a very nice property of the correlation and the covariance matrices. So let's just see how that comes through. So what we said is that this covariance matrix of X is given by 1 over n of x transpose times x. And now I just plug in the singular value decomposition. So this is 1 divided by n, and then I get v times this matrix sigma times u of t, and this is multiplied with u times sigma times v of t. So I'm just using the singular value decomposition. Now this matrix here becomes just the identity matrix n times n. Remember now that this one has dimensionality n times p, and this one has dimensionality p times n. So you see now that when you perform these matrix-matrix multiplications, you end up with v times sigma t times v transpose, which is the same as v sigma squared times v of t. And that, if we now just write it out as a matrix, this is going to be given by the singular values squared down to lambda p minus 1 squared multiplied with v of t. And this is also multiplied with n times n here. Now, these singular values are always organized either as an ascending or descending series. So lambda 0 can be larger than lambda 1, larger than lambda 2, and down to the smallest one, lambda p minus 1, which is larger than 0. Yeah? They can also be equal. They can be equal. You can have degeneracy there. So they can, but it's very unusual that that happens. So these are the singular values, and they are non-zero. You can order them as descending or ascending series. That's up to you. Now, in our case, these eigenvalues, as we said, these singular values are going to be the variances. So these quantities are going to be sigma 0, because you will see now, if you look at this problem, what we have, if I multiply with v from the right, what we have then, so we have the covariance matrix. Let me just bring it up here. So I have 1 over n, and then I have x transpose times x multiplied with v is equal to 1 over n, and then I have v times sigma squared times v transpose times v. And that is the same as an identity matrix of dimension p times p. And then if we then remember that v now contains all the orthogonal vectors, v1, these are vectors, up to vp minus 1. And these vectors are orthogonal. V of I transpose times V of j is equal to delta ij by construction. So this is the singular value decomposition theorem, which says that these matrices, V and U, are orthogonal matrices. It's a very important theorem. It's actually a fantastic theorem. So if I look at that one, and I take 1 over n of x times one of these eigenvectors, suppose I take eigenvectors v of I, this is going to be given by 1 over n of v of I multiplied with the eigenvalue squared. And this eigenvalue is a variance. So this quantity here, v of I, is the same as sigma I squared, where sigma is the variance. So if I do a singular value decomposition, which is actually pretty common in the PCA, you have immediately the eigenvalues, and then you know how to reconstruct everything. And then you would typically say that, okay, let me keep as an approximation those features. So the PCA approximation, the typical one as an example, to keep 95% of total variance. So that means that we sum up all the variances, sigma I squared, from I equals 0 up to p minus 1, but we make a truncation now. So you truncate to keep only those eigenvalues or singular values, which give 95% of the total variance, And that will correspond to a specific number of features. And you saw that in the code examples from scikit-learn, that you could actually put in that threshold, 95%. And scikit-learn does this automatically for you and figures out which eigenvalues and eigenvectors should be included. Okay, so how was the original PCA actually formulated? So this is what you might call the link to the singular value decomposition. But then the question is, can we actually derive this in a different way? And the way which was actually proposed back in 1895, so this is pretty old stuff, was to look at the reconstruction error. And this brings us back to autoencoders. So what is normally called, it has a name, it's called a statistical PCA. And in that specific case, what we are looking at is the reconstruction error. And if you think back to the autoencoders, this looks pretty similar. So we want to minimize what we call J of y, the reconstruction error, which is just 1 divided by n. And then we have a sum of all the data which we have, y of I, minus this y of I tilde squared. And in our approximation, what we had is that this y tilde was given by this linear approximation of VWY, like that. That's what we started out with. And an autoencoder with a linear transformation looks like this. So what we have here is actually pretty close to the standard. So what we will do now is actually to optimize this problem here of I, and then we have y of I minus, and then we have this v tilde multiplied with w multiplied with y of I squared. But now we have to be a little bit careful with dimensionalities here, because this is actually just one component. And here I've written this out as a matrix times a matrix times a vector. But now we have to be a little bit careful here. So if you now think of this object here, what you could say now is that you would like to define an approximation. We want to find a transformation which actually finds the eigenvalue. So the PCA theorem from this reconstruction error gives the smallest reconstruction error if we can find a VW times V, which is given by a vector S. And this vector S is part of a orthogonal transformation, which diagonalizes the matrix for us. So we want an orthogonal set of vectors like this. So I cannot write S0 T times S0. So these are vectors now. This is an inner product. And this is an outer product. So what I want now is to find a vector argmin, an optimization problem, where I actually minimize this reconstruction error. And this is given by y minus, and now I write this as vectors times s. So these are orthogonal vectors. So we assume now that there is a set of such vectors, so that this S, there's a matrix S, which now contains these different vectors. So I'm going to reconstruct that matrix without doing a standard linear algebra problem here. And we want to have a reconstruction error so that the covariance matrix, which has the largest eigenvalue sigma 0, is the one which actually fulfills this problem. So this should be multiplied with y here. So we should put a vector sign and a vector sign there. So this is the quantity I want to optimize. And the way I'm going to set this up now is that these transformations here, which I'm making, should be proportional to this S0 times S0 transpose. And I have made the assumption that S0 is normalized and put equal to 1. So I want to build up an orthogonal basis of vectors, which are also properly normalized. So the way it's done then is to define a Lagrangian. And then we optimize this quantity. So I define a Lagrangian, which is set up as this vector S transpose times the covariance matrix multiplied with S0 plus a Lagrange parameter, Lagrange multiplier of S transpose times S. And then I want to optimize. With respect to S0 and this quantity lambda 0. If I take the derivative with respect to this quantity S0 transpose, so let's do that one. Then I'm getting the following. I'm going to get covariance of X times S0. And that is going to be equal to lambda 0 times S0. So I'm taking the derivative, and the first parameter is just a lambda 0 times 1. So that disappears when I take the derivative with respect to that quantity. Then what I can say next is the following. I multiply this equation here from the left. I'll multiply from the left with S transpose. Then what I get is that S transpose times this covariance of X, no, not X0, but X, the covariance matrix times S0 is then simply equal to lambda 0. And that is the eigenvalue. Of the covariance, as we discussed earlier. And that eigenvalue, lambda 0, is the same as the variance squared. So if I do this now, the quantity which optimizes or minimizes my truncation error or reconstruction error is a vector which has the largest eigenvalue, or which again is the largest variance. And that's the one which reduces my reconstruction error. So it doesn't mean that the reconstruction error will be 0. But what optimizes the reconstruction error is a unitary or orthogonal transformation where the first vector I have set up, this one, is a vector which gives me the covariance, the largest covariance. That optimizes my reconstruction. Now, what I can do next is that this S0 is normally called the first principal component. So this is the largest eigenvalue, which is the same as the largest variance, because the eigenvalues of the covariance matrix are the variances. So this is called the first principal component. Then I can use this Lagrangian formalism to construct the next eigenvector. So what I could say now is that the next is S1. And what I want then is S1 to be orthogonal with S0. So this is a constraint which I'm putting in here. Then I can define a new Lagrangian. And then you will see that this new Lagrangian is going to form the basis for a recipe of finding all these vectors, which we put up here, in a so-called induction-based approach. So let's see now how we can find this S1. So what we would do then is simply to set up a new Lagrangian, which we put up to L equal S1 transpose times the covariance matrix of X times S1 plus, and I have a lambda 1 of 1 minus S1 transpose times S1. So this is the normalization condition, plus a constant, which I call gamma, times S1 transpose times S0. And I want that one to be 0. So what I do now is I take derivatives with respect to S1, lambda 1, and gamma. So if I take the derivative, if you just look at the different derivatives here, let's just take that one, and let's just take the derivative with respect to S1. Now, this is going to include a factor of a half, so I'm dividing away a factor of a half. So I get the covariance of X multiplied with S1 plus gamma of S0 divided by 2, because I get a factor of 2 from the derivative here and also the derivative here, because this is S squared in principle, if these were scalars. And this is going to be equal to lambda times S1. Then multiply from the left. Multiply from left with S0 transpose. Then we are going to be able to simplify this expression a little bit, and we will see now that some of these constants can be easily defined. So if I do that, then I'm going to get S0 transpose times the covariance of X times S1. Now, this quantity which you see here is actually the same as lambda 0 times S0 transpose. This is just the left eigenvalue problem. You have the right eigenvalue, it's a symmetric covariance, is a symmetric matrix. So I can rewrite it like that. And this is then multiplied with S1. And you see now that these ones are defined to be orthogonal. So that should be equal to 0. Then I get plus, and then I have a gamma divided by 2 times S transpose times S0. I should put vector signs here because these are vectors. Plus, so let's just put it like this. And this should be equal to lambda times S lambda 1 times S transpose times S1. Now, this quantity, if I now sort this up, what I get then is that gamma is equal to 2 times lambda 1 minus lambda 0 multiplied with S transpose times S1, S0 transpose. And this quantity is actually equal to 0. So gamma is equal to 0. And then I multiply with S1 transpose and the covariance matrix of X, S1, and this is equal to lambda 1, which is the variance which we called Y of vector 1 here, the one component. So this is again the second largest variance. So now I have the two vectors which are going hopefully to optimize even better the reconstruction error. And then what I could say now is that I could continue doing this till I hit a point where I'm happy with the reconstruction error. That is small enough that I can say, okay, now I stop here. And that could mean that I have 95% of the variance. So this can be done by induction. And by induction, what I could do then is simply to set up induction. Then I can define all the other ones. So I have a Lagrangian where I have a component S of I transpose, covariance X, and then I have my S of I plus the Lagrangian multiplier, and then I have 1 minus S of I transpose S of I plus this additional term where I sum up to I minus 1, and then I have my gamma J, and then I have my SI transpose multiplied with Sj. So I can keep going on and define these different parameters. I will find that every lambda is the same as the eigenvalue of the covariance matrix, which again is the variance. And then I could say, if I now sum up all these variances, I could stop at, let's say, 95%. Now, what you see, if we now go back to the autoencoders and we have a linear transformation, what we are doing here is essentially setting up an autoencoder. So a linear PCA, where you, if we go back and look at this reconstruction error, so if you look at the autoencoder, what we have is the minimization of parameters VW, and then we have the mean square error, and we have Y of I minus, and then we have some function which we call for G, which depends on this quantity, V tilde. There is a function which we call F, which depends on this one, multiplied with the parameters which we ended up with. And if we now choose a linear one, where we have V tilde times W, then these quantities here, if we now look back at the PCA, which we've been doing, this will be the same as a vector S, or rather, a vector of a unitary of an orthogonal transformation of SI transposed. So when we build up this reconstruction error, this corresponds in principle to us to set up a set of matrices defined by the orthogonal vectors of a matrix, which is an orthogonal transformation, which gives us the eigenvalues of the covariance matrix. That is essentially the classical PCA theorem. And it corresponds mathematically to an autoencoder where we have replaced the decoding and encoding part with a linear transformation. That means that we multiply the data with a matrix plus some biases, and then multiply it with another matrix plus some biases. And that gives us essentially the classical PCA linked with autoencoders in its simplest form. Now, when we go to an autoencoder, what we end up with actually is something which is in general much more complicated, because we would deal with a neural network which is highly nonlinear. Now, in the lecture notes, you will find examples of applications. And as I said, I promised to use the MNIST data throughout the semester. And the examples which you will find as programs on the usage of autoencoders are based on an analysis of the MNIST data. But you can replace that with any other type of data set. And if we go back to the Jupyter notebook, so let's do that. And this is where we end today. So one thing I did was actually to upload everything through Google Colab. So let me just increase the fonts here a little bit. So in the examples which you will find here, there are several codes which I have borrowed from the textbook by David Foster. There are also PyTorch programs. Some of them I borrowed from Rashka, but also I've written some of them myself. And in this particular case, if we just skip to some of the first one, because this is just a simple problem where we have some data which we generate. But if we scroll down a little bit, we are now going to the MNIST data set. And in this case, what we are going to do is to set up a typical dense layer. And there is an activation function which I wanted to mention, which is called the Celo function. And I guess you're not familiar with that one. So let me just bring that up. And we will continue a little bit with this next week. So let me just mention what that is. Celo's activation function. That, as I said, there are tons of these functions. So I mentioned the Celo one. So the Celo one is actually a function when x is larger than or equal to 0. It contains just a hyperparameter lambda multiplied with x. And when it's below, it has an exponential, a linear exponential. So this is another one which you can add to the family of activation functions. And in this specific example, we are using this function. I see that my time is over now. So I will just wrap up about autoencoders next Thursday. And then we switch over to generative methods. And I wanted to get started with Boltzmann machines and energy-based models, because some of you would like to deal with that as well. For the project, I mean, for those of you doing a full semester, one single project, just upload a short description of 1 page, something like that, with what you've done and what you're planning to do, so that we get a kind of feeling of where you are. It's very easy to postpone everything. But then June 1 comes suddenly. Okay, guys, thanks for coming. I'm going to stop here, and then we end the discussion of the programs which you will find in the Jupyter notebook. So I will go through some of these programs next time when we round up the discussions of autoencoders.